Good day. Thousands of years ago, it was discovered that heating a liquid to the point of vaporizing or boiling ended up changing it in some manner. Things left in the vapor, some things stayed behind. At first, we were after what was left behind. Then we started desiring what left the liquid in that vapor. Regardless, we needed a container for our liquid in which to heat and use tree trunks to clay or stone, and then some prehistoric peoples who knew how to create these pots from ores. If copper ore was handy, copper was one of the easiest ores to manipulate and shape, and while unknown at that time, could actually trap undesirable character from those vapors. Almost 10,000 years later, copper vessels are still being used for distillation. Let's dig in. Welcome back to our lecture series supporting the WSET Level 3 award in spirits. When we discuss spirits of character, Cognac, complex whiskies, tequilas, mezcals, piscos, and so many more, we are fundamentally discussing distillation in pot stills. This ancient technology, defined by its batch operation, remains the cornerstone of quality and complexity in the world of distillation. But beneath the iconic copper surface lies a highly complex interplay of physics, design, and critical human management. So we're going to dive into the anatomy, thermodynamics, operational models, and regulatory demands that make the pot still the sophisticated engine of spirit production that it is. Our goal is to explain how distillers use these tools to not only create a spirit, but determine precisely what is included in and excluded from that spirit. Nearly all pot stills are defined by four fundamental elements: a heat source, a pot for the liquid, pipes to carry the vapors, and a condenser. But it's the design variations that dictate the style of the spirit. One is our still height and reflux. The most obvious variance is height. Check out the advanced distillation lecture to brush up on temperature gradients. These tall stills will naturally have potentially cooler still heads, as they are farther from the heat source, which inherently promotes more reflux, where our vapors condense and fall back into the pot repeatedly. This increased reflux effect separates our fractions more and can generally lead to a lighter, purer style of spirit. That said, the fill level and the speed of the run matter just as much. Remember that the temperature in our pot is always increasing, since the ABV in the liquid is decreasing and the boiling point has to increase. Time is money, and if you rapidly increase the heat or really fill that pot up, you will squeeze that temperature gradient, no matter the height of your still. Then the piping, we have a piping angle. Even the angle of the pipe linking the pot or line arm to the condenser matters. If the line arm angles downward, any condensation flows straight into the condenser. Conversely, if the line arm is angled upward, condensation flows back into the pot, continuing the reflux process right up until the point the vapors enter the condenser. And then we have condenser and condenser technology. Vapors must be cooled by a coolant, typically water, in a heat exchanger. One of the original condenser types is the worm tub. This traditional design uses a single coiled pipe, the worm, submerged in a large vat of cold water, which is the tub. Then we have our Shell and Tube Condensers. This is today's most widely used design. Coolant runs through narrow pipes or tubes enclosed by a shell. Vapors enter the shell and condense on the cold pipes. The Shell and Tube design is more energy efficient and compact. And crucially, if the pipes are copper, they offer a much larger surface area for copper interaction, allowing for a greater removal of those sulfur compounds and resulting in a lighter and cleaner spirit style compared to a worm tub. Then we also have bowl of water condensers, found commonly only in Mexico for Mezcal. These are effectively a variation on a deflegmator, sitting directly on top of small stills. Vapors condense on the underside of the cold water bowl before being collected. Now, they're not really scalable, but they can produce outstanding spirits. Let's move on to our thermodynamics, or the power of heat. How heat is applied profoundly influences the spirit's character, dictating not just efficiency, but also chemical reactions within the still. The original method, our direct heat, often utilizes wood, coal, or gas. Some distillers, notably in Cognac, are legally required to use direct heat. Others use it because experimentation with steam could not recreate their desired spirit profile. Direct heat, if well managed, increases the level of Maillard reactions and esterification, which significantly adds flavor to the final spirit. However, this direct heat does carry scorching risk by creating hot spots. This increases the risk of scorching any solids settling at the bottom of the pot, which introduces unpleasant flavors. Solutions include using gas burners, which are easier to control than wood or coal, and also employing mechanical scrapers or stirrers called rummagers to keep those solids moving in the base of the pot. Now, steam, or even indirect steam heat, is the most widely used heating method today, generally being less expensive and easier to control. Steam is generated externally and heats the still surfaces in contact with the liquid without ever touching the liquid itself. Now, jackets, these are the most common modern design. A jacket is mounted externally, providing a very even heat over the largest possible surface area. This efficiency and lack of hot spots minimizes the risk of scorching. Then we also have coils, where steam passes through submerged coils. These are kind of less common now due to the risk of scorching. And then we have reboilers. This is an external heat exchanger where the liquid is pumped out of the still, rapidly heated, and recirculated back. This also minimizes scorching risk due to constant rapid movement. Then we can also have direct steam heat, or steam injection. Now, this is necessary when the still contains a high level of solids. For example, in the production of pomace spirits like grappa, indirect heat is insufficient. Steam is injected at high pressure into the base, forcing its way through the solids, causing volatile fractions to evaporate and pass out of the still. We also see this used in Baijiu. So, our pot stills operate via batch distillation. To understand the fundamental goals, we're going to look at the Scottish model for double pot still distillation, a widely documented and widely used approach. The primary challenge is that distillation cannot simultaneously achieve high concentration and collect all the ethanol. So we're doing this repeatedly. Our first distillation are called the stripping run. Here our initial alcohol liquid is, say, typically around 10% ABV. The main goal is to concentrate the ethanol and volatile fractions by removing most of the water and all of the non-volatile group 4 fractions. Distillers are not aiming to select group 1s or heads or group 3 tails. They're not those fractions. We're not after those yet. Well, some people do. The distillation continues until the liquid flowing from the condenser drops to about 1% ABV to ensure maximum ethanol yield, as discarded ethanol is usually taxed. The collected liquid, called low wines, is typically around 25% ABV. The non-volatile liquid waste left in the still containing group 4 fractions is discarded, Or since we often have some fatty acids left over, we can use this back set to send back to the fermentation stage, providing not only acids, but some nutrients for the yeast. Then we go to our second distillation, usually called the spirit run. The low wines are mixed with the recycled heads and tails from the previous run in the spirit still, raising the liquid strength to about 25 to 30% ABV, and that's placed in the spirit still. The main objective is to create the final spirit by concentrating and selecting the group 2 fractions. We do this through cuts. The liquid flowing from the condenser is collected in 3 distinct parts over time, based on fraction volatility. In our heads, or group 1s, the initial flow, these highly concentrated group 1 fractions, these are the most volatile, is only for a few minutes, as the total volume of these group 1s is pretty small. Once these unwelcome group 1 fractions pass out, the flow is redirected, and this is the first cut. This commences the heart cut. The heart is collected for several hours, containing a high concentration of desired group 2 fractions, including ethanol. And the heart comes off the still at about 75% ABV. Again, that's an average. Then we make a second cut or tails cut, redirecting the flow back into that heads container. Now the tails are highly concentrated in group 3 fractions. These are the least volatile ones to leave the still. And collection again continues until the spirit flowing is about 1% ABV to really maximize ethanol recovery. Now, remembering the fractions are not perfectly separated, so we have ethanol that ends up in both heads and tails. Therefore, the heads and tails are typically recycled into the next batch of low wines to reclaim some of that valuable ethanol and the group 2 fractions they may still contain. Distillers have 2 primary tools to shape their spirit cut: still management, the cuts, and temperature management, or kind of the reflux side of things, those inclusions and exclusions. While high concentrations of group 1 and 3s are undesirable, small quantities of them can add desired complexity. Distillers may intentionally include small amounts of group 1s for an attractive aromatic lift, or small amounts of group 3s for some palate richness and extra complexity and texture. Group 4 fractions are pretty much excluded due to the first distillation. The major challenge in the second run is eliminating high concentrations of group 1 and 3 fractions while minimizing the loss of desired group 2 fractions. Cuts determine the proportion of group 1 and group 3s that get included. A narrow cut, this means cutting late to the heart, excluding more heads, and cutting quickly to the tails, excluding more tails. The result is a purer, smoother spirit because a greater proportion of group 1 and group 3 fractions are excluded. Then we have a wide cut. This means cutting sooner to the heart and waiting longer before cutting to the tails. This includes a greater proportion of group 1 and group 3 fractions, resulting in a spirit with more complexity, but also textural sharpness. Now, the temperature difference between the top of the still and the boiling liquid significantly affects separation. If we have a small temperature difference, this will happen in shorter stills or during vigorous boiling. The distillation will be quick, but the peaks in fraction concentration are compressed, making it much harder to separate group 1 and group 3 fractions from the heart. If we have a large temperature difference, this is achieved using a tall still or maybe specialized equipment like a defleg. These are often found in hybrid stills. The distillation is slow, but the peaks in concentration are more spread out, making it easier to exclude group 1 and group 3 fractions and produce a purer style of spirit. Despite its limitations, the pot still is favored for its reliability in producing outstanding, characterful spirits. Distillers have centuries of experience crafting specific styles. Making fundamental changes to their copper equipment that's a risky proposition. However, 3 key operational challenges are always around. We have pretty high operating costs. Pot still batch distillation involves many repetitive tasks, historically requiring large workforces, although many of the processes are now automated. We also have the inability to rectify highly. Pot stills cannot produce highly rectified spirits like 90% ABV or more. Even with triple distillation, the final spirit strength is usually only around 80% ABV. Producing a neutral spirit requires the rectification plates found in column stills. The other thing we have here is a constant buildup of those group 3 fractions. We're recycling the heads and tails. This is a necessary step to reclaim ethanol. Leads to an unavoidable gradual buildup of group 3 fractions in the subsequent batch. The new batch of tails collects the group 3 fractions from the old tails and the group 3s from the new low wines, causing the total volume of tails to increase over time. Distillers have to employ specific methods such as selling off or discarding accumulated tails to manage this buildup and maintain the intended spirit style. Those heavier alcohols or fusel oils can also separate out around that 25 to 30% ABV. So if collected after the stripping or first run, they will float to the top of a tank if it cools a little bit, and you can pull from the bottom to leave those behind, or at least some of them behind, and then dump those out before the next spirit run starts. And again, where, when, and how much are all distilling choices depending on desired style or economic considerations. So let's just quickly overview and look back and consider what it takes to have a successful pot distillation. Ensuring quality begins with selecting appropriate raw materials, minimizing contaminants, and careful processing. For malt whiskey, distilleries, they look for low nitrogen spring barley that provides high potential alcohol yield and is easy to process. Malting has to be done well to ensure that the starch is accessible and that the enzymes necessary for starch hydrolysis are developed. Kilning needs to be done gently to minimize damage to the crucial amylytic enzymes. Milling needs to be done properly to achieve the best practical grist composition for the specific mashing system being used, minimizing damage to the husk, which kind of acts as a filter medium, while also ensuring no unbroken grains still remain. Mashing temperature now is critical and must be kept constant because temperatures above 65 C cause rapid deactivation of essential malt enzymes, leading to suboptimal starch hydrolysis and even incomplete fermentations. Then during fermentation, we have choices that directly and substantially impact the congener profile and spirit yield. We need suitable yeast strains with good ethanol, temperature, and pH tolerance. In most cases, we're wanting a rapid start to fermentation to avoid excessive bacterial contamination. The goal is to achieve maximum theoretical alcohol production, aiming for a small amount of yeast growth. If we cut fermentations too short or rush the process, we can get a gassy wash that is difficult to distill. And of course, temperature must be controlled to keep yeast functioning properly. However, in some processes, a late lactic fermentation is allowed to bloom, which if managed properly contributes desirable flavor and aromatic compounds to the spirit. And then again, those wash stills must be heated gently, especially at the start, to prevent charring of those wash solids onto the heating surface. This burn-on reduces the heat transfer. Excessive heat, an overloaded still, or a blocked condenser can cause the still contents to boil over into the safe, damaging instruments and contaminating low wines. The use of copper is fundamental to spirit quality in European pot stills. But copper is not universal, and quality spirits are made in clay as well, with porous clay able to trap some group 3s. Head to the Advanced Agave Spirits and Shochu lectures for a deeper exploration there. And while we've been talking about these Scottish-style pot stills, the processes for clean, quality spirit production in batch distillation are similar regardless of what the pot is made of. Now we have, of course, our cuts. The alcoholic strength of the low wines should not exceed 30% ABV to prevent those heavy oils from dissolving completely into the liquid layer. If that concentration exceeds 30% ABV, it can actually lead to what's called a blank run. It contaminates the entire distillation system and makes collection of any potable spirit impossible. So our pot still is far more than a simple copper kettle. It's a highly complex, batch-operated system where every detail, from the angle of the pipe to the type of heat source, is a lever used by the distiller to define flavor. Understanding the physics of reflux and the management of cuts is key to understanding the rich, complex, and distinct spirits that only this traditional method can produce. See you next time.